Then you use values for all surroundings for that. Every calculation is sort of concatenated.
So we have only 30 minutes. We have only 30 minutes or 35 minutes. So we will talk, just give an introduction to those convolutional neural network, and after that, I mean next week and the week after, we will finish CNN and RNN, so we can have enough time for working on projects. So, so the plan now is to combine your project into one project, and we can get more mature results. I guess it will be more useful and just work in groups. It would be nice to work in groups, and I wish if we can build some models here in the lab. So if we have two screens here in the lab, for example, so you can build a model. Maybe one group working in those license plates, maybe someone else. If you can work with face recognition, it would be nice. We can build face recognition and we can put it here in the. You can build a demo in the lab and make it working here all the time. You can check if the machine will be able to recognize us or not. I wish also if we can do some adversarial attacks. It will be very nice if it is targeted, for example, or untargeted. It will be very useful. So we can classify people as Donald Trump, for example.
Yes, I like him.
You like him? Yes.
Because of his sanction against Iran.
Yeah. So anyone like Biden? Joe Biden?
No, Joe Biden is not good. Because of the Iran.
Yeah.
Okay. I just see this position, I'm Iranian.
Mm-hmm.
If Joe Biden is elected as president, the situation of Iran will be continue as bad as before.
Mm-hmm.
Trump, I think, helped to Iranian people to, for example, remove the current situation.
I don't think that will be the case because Joe Biden was vice president when Obama negotiated the nuclear deal and gave Iran back the money.
Yes.
So Joe Biden will reinstate the nuclear deal that Trump scrapped, and things will be fine and Iran will not be sanctioned.
Yeah. I agree with you.
Yeah.
It's good for removing sanctions. It's good for removing sanctions, but it's not good for the future of Iran.
So you
well, if they remove the sanctions and you are able to sell oil and have all your money and use the international monetary system, everything will be fine.
But the sinister guys will be remain.
Well, that is an issue internally for you to resolve, not for him to resolve. You will have to do what to do to have a new regime, but internationally you will not be oppressed anymore.
Yeah. You are Iranian?
No. I'm Nigerian. I just follow the news a lot.
Okay.
Yeah. But I have a lot of Iranian friends. They're really nice people.
In the Middle East also have lots of dictatorships, and they are fully supported by, I guess, by Trump. Yes. So I'm not supporting Trump at all. Because those people will continue. I mean, he provides support for those dictatorships.
I guess we should terminate this video session.
Okay, so Hamad, we will go for CNN.
I guess it is going more political, so it should be offline, I guess.
That CNN different from that CNN.
Yeah. Yes. So CNN here we need to learn higher order features in the data by convolutions, and we describe those convolutions, how those convolutions will be done. Convolutional layer is responsible for systematic applications of one or more filters to an input. So it will be automatically applied those. It's a systematic applications of those filters or kernels. How can we get those kernels? If you are working with image processing, you will decide what kernel you are interested in, right? It could be those edges in X direction, Y direction, we don't know. So the architecture consists of 3 types of layers in convolutional neural network. We need to have an input layer. This input layer, it will accept 3D input, such as RGB images, for example. It could be 1D, it could be 2D, it could be 3D, correct? After that, we will have some features, some layers for extracting feature, for feature extraction. So feature extraction layers, it will be repeated sequence of convolution and the pooling layers. So we will have a stack of convolutional layers for extracting features. This is the part which we can import from other program. This is the part where we can use transfer learning. Transfer learning, it means we can import this feature extraction layers from another domain into a new domain, right? And finally, we will have the classification layer, which we call it fully connected layer. This classification layer, this is the brain, in fact. Classification layer, this is the one which will make decision. There's no difference between this one and the shallow learning, because in shallow learning, we have 1 or 2 layers for making a decision, right? So what is different here? It's the convolutional layers. And those convolutional layers, the idea behind it is to try to extract features automatically by applying those filters and also updating the weights of those filters, right? So, I mean, in this example here, so we have here some filters. The filter consists of some numbers or weight values, it's just weight values. So if you want to extract edges in the X direction, you need to use one. If you want to extract across Y direction, you need to use another filter and so on, right? Those filters, I mean, they are designed, they are static. Those numbers are static. Maybe you can change it to fine tune it, for example. But in case of convolutional layers, we will get those weight values automatically, right? We will get those weight values automatically. You just need to decide how many kernels we need to extract, how many feature map we need to extract. So it is a kernel size which you need to decide, and how many feature maps you want to get. Correct? This is the whole task. And so it's applied like repeated sequence of convolution and the pooling layers. Feature map, pooling, and we will repeat this one maybe several times, right? The rest will be just hyperparameters, and after training it, maybe you can transfer it from one application, from one domain to another domain. So we will have an input image. This input image, it could be 2D image or 3D image, right? It could be 3 channels or 1 channel. It could be a signal, it could be text, it could be anything, it could be time series. We will have some feature maps. The number of feature maps, it's user defined. You need to define how many feature maps you want to get. And if you need the size of the feature map to be the same size here, we need to use 0 padding, correct? Stride, the step, because we will apply this, we will apply those filters. We will scan the image from top to down, right to left, left to right, and top to down, right? So the step will be the stride. The stride will control the amount of overlap which you want to keep. And after that, we will use pooling layer, for example. This pooling layer. Those pooling layers, it will reduce the dimension of the feature maps. Why do we need it? It's for overfitting, correct? So if we can reduce this one little bit, and after that get new feature maps, max pooling or average pooling again to reduce the size. So in this case, we can. It's meant for overfitting. So we just agree that convolutional layers, it's a stack of layers with convolutional layers and pooling layers and so on, right? If you want to use dropout, you can just do it. Maybe dropout, we can use dropout here in the classification layer. At the end here, we will have a set of feature maps, and those set of feature maps, we will flatten it because I need to apply it to fully connected layer, correct? So we need to flatten this one and just use a number of fully connected layers here. And at the end, the number of classes, number of units will be the number of classes. So for sentiment analysis, we need to have 2 outputs, yes and no, positive, negative, right? For this Reuters data set, we will have 46 topics. So we need to have 46 neurons in the output, right? And of course, you can, if you will use 2 fully connected layers, maybe the first layer, we can use ReLU for activation. The last layer, if it is probability, you can use softmax or, correct? So So at the end, we will have fully connected layers, and we will get the output here. It will be conditional probability of y given x, correct? It's conditional probability. So probability of class 1 given this image, for example. So this is possible. So the building blocks of convolutional neural network, we have 3 types of layers. We have convolutional layer, pooling layers, fully connected layers. So now we know the main building blocks of any deep learning or convolutional neural network, right? We have an input layer, convolutional layers, pooling layers, fully connected layers. Convolutional layers, it's composed of filters and feature maps, correct? So we need to decide how many feature maps we need to get. Filters or kernels, what is the size of the kernel, correct? So if you want to get 64 feature maps, we need to select 64 filters or kernels. What is the size? So this is one of the decisions which we need to make. 3 times 3, 5 times 5, 7 times 7, 9 times 9. So it's according to the image size, because we will scan the image. We will scan the image using this filter size. Correct? So how much time? The stride, it's the step. If it is 1, it means we will move 1 step between each activation, because in fact we apply this filter to one part. We will make an activation 1 time, and after that we will move it 1 step. New activation, 1 step, new activation, 1 step, new activation. So do you know how many calculations we will do? Too much calculations. So if you want to reduce the number of calculations, you can increase the stride size, the step size. If it's a 3, for example, so we will do less number of calculations, less number of activations. Because at the end, each filter size, you can just imagine each filter size will be a neuron with number of weights. Number of weights will be number of elements of each kernel. If it is 3 times 3, we will have 9 inputs. So those 9 inputs will just go through, it will scan the image, and we will move with the step size. The step size will be the stride. If you will have step size equal 1, which is a default, by default it's 1 in fact. When it's 1 by 1, in this case, we will just take 1 activation, move 1 step, another activation, 1 step, another activation. So you can calculate how many times of calculations or activations for in each image, correct? If you feel that it takes too much time, you can just increase the stride size. The step size, you can increase the step size to reduce number of calculations or number of activations. But just remember, it's how much overlap you want to keep also, because when we move 1 step, we have some kind of overlap. So we scan some parts more than 1 time, twice, for example, right? Which gives more weights to the information in that part. So filters, the filters are essentially the neurons of a layer. Each filter is a neuron, correct? Each filter is a neuron. So when we select 64 filters, it means the number of neurons will be 64. And that is why when we calculate number of weights, it will be 64 times number of elements in the filter. If the filter is 3 times 3, it will be 3 times 3 times 64, plus another 64, which is the bias. So each filter will be 1 neuron. They have both weighted inputs and they generate an output like a neuron. It has some weighted inputs because it will be those omega values, those weight values multiplied by the pixel values of the covered part of the image, right? So just all those weights multiplied by those pixel values, and just taking summation and adding bias value and do activation and calculate output, right? The input size is a fixed square called batch or receptive field. I mean, the size of this receptive field, it will be the size of my filter, because we cover part by part and move step each time. If the convolutional layer is an input layer, then the input batch will be pixel values. If the convolutional layer is an input layer, if it is an input layer, so we will apply it to the input, to the pixel values of the input image. If they deeper in the network, so if it is inside, if it is a second layer, for example, then the convolutional layer will take the input from a feature map from the previous layer, which is also pixel value, because we generate a pixel value. We will generate a feature map will be an image, correct? So, but if it is the input layer, we will apply it to the input image. If it is deep, it will be applied to a feature map, not as original, not the input image. Yes. Feature maps. What is the feature map? The feature map is the output of one filter. So each filter will generate a feature map. If you're applying this one here, for example, if we're applying this one, if we try to extract the edges across the x-axis or y-axis, we apply this filter or this kernel to the image, generating a feature map. So each feature, in fact, each filter will be applied to the image, generating a feature map. So the same will be here. So the feature map is the output of one filter applied to the previous layer. A given filter is drawn across the entire layer, moved 1 pixel at a time by default. If you want to change it, you can change it. This is a stride. Each position results in an activation of the neuron. Each time, each position in each, we will apply it in each position and do one activation. Weighted sum, activation, weighted sum, activation each time. And the output to be collected in the feature map, and the output will be collected in the feature map. So we'll apply it to the input image or to the feature map, previous feature map, and we will make those weighted sum, activation, and the output will be allocated in the new feature map. If the receptive field is moved 1 pixel from activation to activation, then the field will overlap with the previous activations by field width -1, correct? So we'll have some kind of overlap. So if it's a 3 times 3, and we move 1 step each time, so we will have 2 overlap. It will be field width -1, right? So we'll have a kind of overlap. And the distance is that the filter is moved across the input from the previous layer. Each activation is, we have this stride. So the stride will be the step size. As I told you, if you want to reduce number of activations, number of calculations, number of updates, you can just increase the stride size. But when you increase it, you will reduce the overlap. So you can say if the filter size is 3 and the stride is 3, for example, it means I will apply a receptive field here and I will move 3 units, apply it, so I will not have any overlap or any correlation between activations. Maybe it's important, maybe it's not important. So we need to keep some of overlap, in fact. It's very important to have continuity in the feature map, right? So zero padding is used to invent mock inputs with 0 values for the receptive field, not to read off the edge of the input feature map. If you don't have 0 padding, what will happen? The feature map will be if it's according to the filter size. So if the filter size is 3 times 3, for example, so in this case we will lose 1 row, 1 column, 1 column, 1 row, correct? So in this case, the feature map will be 2 pixels from each. I mean, the height and the width will be 2 pixels less, right? If the filter size is 3 times 3. If you want to keep the feature map, if you want the feature map to have the same size as the original image, in this case, we need to use 0 padding. 0 padding, we will just add a number of rows, number of columns with 0 values. We will add some 0 pixels on top and in the left and right, top, bottom, left, right. So the output feature map will be the same size as the original image. This is very important when we have important information. This is only for the input image, I mean, correct? Only for the input. We don't do it for the feature map, right? And this is when there are important information across corners and edges, I mean, around the perimeter of the image, when there are some important information which we don't want to lose. So in this case, we can use 0 padding, right? Mm-hmm.
You use CNN for other things than image.
Yes, you can use it for.
In this case also, you are actually using a filter, but it's not image, it's
yes.
something else.
Yes.
And then I guess it's really important to, because often when you think about pictures, then the edges are not that important.
Mm-hmm. For
other types of information, if it's not a picture, then the information across the edges can be more important.
Yes, but we need to have an example. How can we apply the filter in 1D, right? So when it's time series, for example, it's 1D, not 2D, for example. So I really want to 1D, it will be one vector, not a matrix. So do we need to add zeros? No, because we will apply it. Maybe you will
lose the first and last.
only first and last.
Yeah.
Yeah. Correct. So which might not be very important, right? It's not big deal when it's a time series. Because when it's time series, for example, we have stock price, for example, which is like this one. So I will apply maybe this one. Correct? So we will lose maybe some value here. So just need to add a zero value here. And is it zero? What value should we use here? Zero value? It could be zero value.
Weighted average?
Huh?
Maybe you should count the weighted average and
could
predict the...
Yes. But the filter size will be like this one. It will be, for example, 3 times 1, not 3 times 3. It will be 1D. Correct? So we will apply this one, and it will move also with some stride. Correct? Like this one, etc. So we can apply it in 1D, like in MNIST dataset, it's 2D. In RGB, if it's a CFAR 10, for example, CFAR 100, so we need to have 3 times 3 times 3, because it's RGB image, right? And so on. So it could be more complex when we are working with video, for example, when we have some frames, many frames, right? If you have 5 frames per second, and we need to consider if it is time, because maybe in video, we have frames, we have time, so it will be really more complex, right?
Is it also using numerical data, or it's not worth it?
No, yes, numerical data. If you are working, we have an example here for a time series, for example. If you are working with a time series, we need to predict, stock price, for example, and so on. So it's a time series. So in this case, the filter size will be 1D. It will be, instead of working with a filter size which is 3 times 3, it will be 3 times 1. And we will apply it, and we will move it with a step. So in this case, instead of having, we don't need to add the first, we don't need to add zero, for example, 0 row and column from each side. Or just maybe the first value will be 0. Only the first value in the time series, and maybe the last value, right? So each position results in an activation of the neuron, and the output to be collected in the feature map. The output will be collected in the feature map. If the receptive field is moved 1 pixel from activation to activation, then the field will overlap with the previous activation by field width -1 input values. The distance that the filter is moved across the input from the previous layer, each activation is a stride. This is the step side which we need. And as I told you, the stride will impact amount of calculations, the amount of activations, the number of activations, and the overlap or correlation between different receptive field. Zero padding is used to invent those mock inputs with 0 values for the receptive field, not to read off the edge of the, if we need to keep the edges, if we need to keep information in the edges, because otherwise we will ignore it. So this is an example. We have an input, and we have a kernel, which is 2 times 2, and we need to apply this kernel to generate a feature map. So this one, it's the input image. This one, it's the kernel, and the kernel size 2 times 2, and this is the feature map. So how can we generate this one, right? So in fact, this is the image. Do you see? This is my image, and we use the 0 padding. So we added one row from top, 1 row of zeros in the top and in the bottom, and 1 column of zeros from left and right. We will start from top left, and each time we will move 1 step or 2 steps with a stride, right? So we will apply this one to this one, correct? Just multiply each value by each value. This is the weight values, in fact, which we need to learn. So at the beginning of the learning process, we will initialize those values with random values. So just it would be 0 times 0, plus 0 times 1, plus 2 times 0, plus 3 times 0. So we will get this weighted sum. We will apply it to the activation function, and we will put the output value in the respective place in the feature map. So it will be here. When we use the zero padding, we have the same size. The feature map will be the same size as the original image. And we will do it. We will do it here. We will move one step, another step, another step. If the stride equal 1, right? So in this case, it will be 4 activations. To generate this one, we will have 4 activations. And we will go back here. We will go one step down. So it will be here. 1. So it will be 4 times. So it's 4, 4. This 4, 4. So it will be 4 times 4. So it will be 16 activation if the stride equal 1. Right? So we will scan it using this filter. And of course, we will generate a feature map. We will have another filter, and another filter, and another filter, and so on. So each kernel or each filter will generate a new feature map, right? So zero padding, when applying the convolutional layers, we lose some pixels around the perimeter of the input image. We lose some information. It can add up for successive convolutional layers. If you are using successive convolutional layers, and each time you are losing some of those perimeters, some of the pixels around the perimeter, and if you are just doing it 3, 4, 5 times, we will lose a lot. Correct? So at some point, we will lose all informations around the perimeter. One solution is to add pixels of zero values around the boundary of our image. We're just adding those zero padding. So in this case, the feature map will have the same size as the original image. Stride, by default, the filter slides 1 pixel at a time. So by default, it's 1 by 1. Sometimes either for computational efficiency, as I told you, it's number of activations, or because we wish to downsample. If you want to downsample, we move our window more than 1 pixel at a time, skipping the intermediate locations. Because if stride equal 1, what will be the size? So if I selected the stride equal 1, so I will do it here 1 time, and after that I will move here, and then I will move here. So what will be the size here? That will be 3 times 3. Correct? Because we will go back here, we will do one more calculation here. So maybe it will be like, so if we need to downsample, correct? We can increase also the stride.
The slides on Blackboard is different from the one that you are showing.
Okay, so I will upload it. Yeah. Because I uploaded it to Blackboard and I revised it, and I feel that I need to make some changes. So, so if you need to make it more efficient computationally, right? And also, if you want to downsample, you can just select different stride sounds. So, max pooling. What is max pooling? Pooling layers. The pooling layers downsample the previous layer feature map. If you want to downsample, downsample the previous layers, we can use max pooling. So, for example, here we have a feature map. Because max pooling, we apply it to the feature map, right? So. Okay, so this is pooling layers. So this one, it's a feature map, and we will apply 2 times 2 max pooling. When it's 2 times 2, we will, if it is max pooling, we will apply it here. We will take max. Max will be 4, right? Very simple. We will move 1 step. So we will move here. We will take max. It will be 5. We will go back here. What is max? It will be 7. We'll go here. What is max? It will be 8. So it's downsampling, right? So now the feature map was 3 times 3. Now the new feature map, which is 2 times 2. So it's downsample, right? So it's like getting the most important features again. Remember PCA, Principal Component Analysis, or autoencoder, for example. It's like this. We downsample the feature map. When we downsample the feature map, we will reduce model complexity in the classification layers. Classification layers will be less complex, correct? So it's like to a way for avoid overfitting. So the pooling layers downsample the previous layers feature map. Pooling layers follow a sequence of one or more convolutional layers and are intended to consolidate the features learned and expressed in the previous layers, like summing, take summation or something. So they compress or generalize feature representation and generally reduce the overfitting of the training data by the model. Generalize or compress, like a compression, correct? So we try to get the most important pixel values. When we do this max pooling or average pooling, we try to get the most important information from the feature map and downsample it. And it's a way for to reduce overfitting. So they have also receptive field, often much smaller than the convolutional layer. The stride or number of inputs that the receptive field is moved for each activation is often equal to the size of the receptive field to avoid any overlap, correct? Pooling layers are often very simple, taking the average or the maximum of the input values in order to create its own feature maps. So the pooling, it does not have any parameters. It does not learn anything from the pooling layer. So the pooling layer, the input will be a feature map, the output will be a downsampled feature map. But there is no features, there is no weights. We don't have any weights. It's only stride. It will be almost the same stride of the previous layer. It will move with the same value, and it will just apply this very simple calculation, taking a maximum, taking average of the receptive field, right? When it's 2 times 2, it will be reduced, it could be 3 times 3. So the reduction will be more, right? And it's a way for reducing overfitting. Are we done today, or what time is it? We are done. Okay, what time?
16 past 12.
Okay, so now I've finished for today. It's just, we will finish with this one for fully connected layer, because this is the last part for building it. And next time we will take more examples. We will try to work with time series. We will work with images. We will try to work with different data sets. So even also, if you can try, for example, AlexNet, we need to try to use AlexNet, because we can import this part from AlexNet and apply it as a feature extraction part from AlexNet and use it for different applications. So here it's a fully connected layer. So in the end, we have input volume. This input volume, it's an image or data which we are working with. We have some convolutional layers and max pooling, for example, to reduce the size of those feature maps down sampling. And after that, we will flatten. This flatten, it's nothing, just a flatten. This one, it's a square. I mean, those feature maps are squares, for example. We will flatten it to convert it into a vector. And after that, we will have some fully connected layers, maybe 1 layer, 2 layers, correct? If you have 2 layers, for example, maybe the first one, it will be RELU activated. The last one, it will be softmax, for example, or because we need to calculate probability, right? This one, number of classes, number of units will be number of classes, correct? This one, it's just up to you. It's a hyperparameter. So the fully connected layers are the normal, flat, feed-forward neural network. It's just feed-forward, just normal, like shallow learning. These layers may have non-linear activation functions or softmax activation function. It's up to you to select, right? Fully connected layers are used at the end of the network after feature extraction and the consolidation. This consolidation from max pooling. So pooling layer, it will make some consolidations. They are used to create final nonlinear combinations of features and for making predictions by the network. So it will make the final decision predictions. So the first part, the first stack of layers, convolutional layers for feature extractions. And after that, we will have flatten layer here to just make it as a flat, as an array. We will apply those values to the fully connected layer. Fully connected layer, it's feed forward, just normal feed forward for prediction. And I guess next time we can just take some examples. And we have some examples for next time. From Keras, we need to do those. We will implement convolutional neural network using Keras, which is very, very good. Keras and the PyTorch are perfect for doing this. But Keras, I'm more familiar with Keras. So but it's up to you to select. So we will take some more examples in the next week, for example. How can we do it? And yes, so next time we will work with Keras and we will try to develop some examples. We will try C410, C400, for example. Yes. So do you have any questions for online? Any questions?
Do we have a lab today?
You need to arrange this with Meng Tao, please.
It's Wednesday.
It's Wednesday. Did you move it to another day?
On Wednesday at what time?
It's usually on Wednesday.
It's Wednesday.
Yeah. This. Okay.
From 12?
No,
It has been
it's, later.
Later. It was maybe from 5, from
2 p.m.
4.
2 p.m.
2?
It depends. You have to check Blackboard, but usually it's 3 to 6.
Yes.
But sometimes we can move it from 2 to 5. But
Yeah, because Meng Tao, I guess it's okay for Meng Tao to move it in any time. So just please discuss this with Meng Tao because he is in charge.
yeah, he's always posting such kind of information on Blackboard.
Okay, very good. So please just check Blackboard for this.
Okay.
Yeah. And work in the project, please. Now we changed the project into one big project. We need to end up with a demo. We need to have a demo. And if you can work with your own data set and try to write a paper, for example, from the course, it will be very, very good. So, but we need to build a demo at the end. One demo maybe with those driving, car license plates, for example. Maybe also if we can do some demo for face recognition, it would be very good. We need to, I shared with you those links for adversarial examples. If we can do it, it will be great. So we can have a nice demo here, because if you will just try to recognize the driving license plates correctly, it's okay, but it will be more exciting if we can misclassify it, if we can force the model to misclassify it to something else. It will be really very exciting.
How do you take care of the data?
Yes.
I can put also some links in the Blackboard for the rest of the video to try to use the same.
But it's okay.
But in this case, you need to go for PyTorch, I guess.
Yeah, I'm looking into PyTorch.
Yes, because they have developed those tools in PyTorch, much easier to calculate those gradients in PyTorch. They have some tools already there, so don't need to do it from scratch. Okay, thank you very much for today. And I also shared a link with you, please, if you can vote for it, if you like, if you feel that it's a... Okay, thanks. Thank you very much for today, and we will meet again next week. And please check the lab time with Meng Tao. And if you have any questions, just ask Meng Tao to do some implementations. If you are working with a project, for example, just you can work in the project in the lab. So just involve Meng Tao in this project. And
yeah, we have to win a lot of practical projects.
Okay, I mean for this project, for the course project, for those driving license plates, it will be good project for working in every week in the lab, so people can share knowledge and experience.
That lab is related to the circular economy and sustainability.
Oh, this course.
Yeah.
Okay, thank you very much, and we will meet next week.
It's